Renewable energy sources like wind and solar are intermittent, meaning they only produce energy when the wind is blowing or the sun is shining. This intermittency poses challenges for the power grid, which was designed around large, controllable electric generators. The balance between electricity supply and demand must be always maintained to avoid a blackout or other cascading problem. Here are some solutions to overcome these challenges. Investing in new grid infrastructure and tools. This includes tools that can handle the variable nature of renewable energy. Retaining more dispatchable generators. These are power sources that can be turned on or off, or can adjust their power output in response to an order. Increasing storage and demand-side flexibility. Energy storage technologies like batteries can store excess energy produced during periods of high renewable energy generation and then release that energy during periods of low renewable energy generation. Implementing the right set of incentives. This ensures that various stakeholders act to address the challenges. Using more renewable energy. A mix of offshore and onshore wind, along with contributions from solar power, could provide reliable and cost-effective power flow during all but a handful of days in a hypothetical 4-year period under study. Pumped storage. This is a type of hydroelectric energy storage used by electric power systems for load balancing. Hydrogen storage. This is considered for long-term energy storage to resolve seasonal variations in electricity generation. Here in this table, you can see different types of renewable energy. The field of renewable energy technology encompasses various methodologies, including solar, wind, geothermal, biomass, and hydropower energy generation. Integrating renewable energy into the electricity grid is crucial to addressing global climate change. Renewable energy sources such as solar and wind power have gained significant traction in the global quest for sustainable energy. However, the intermittent nature of these sources presents a challenge in balancing energy supply and demand. To fully maximize the potential of renewable energy and ensure a reliable and resilient power grid, efficient energy storage solutions are crucial. In this video, we delve into the significance of renewable energy storage, explore the challenges posed by intermittent, and highlight innovative solutions that are overcoming these obstacles. Factors affecting the cost of the energy system. This figure shows that the system load factor, renewable proportion, and grid connection off-grid degree affect the energy system cost. An increase in load factor reduces the cost of energy. Increasing the renewable proportion minimizes the application of traditional expensive energy sources. The off-grid energy system can sell excess power to the grid, thereby reducing energy costs. Challenge of intermittency. Renewable energy sources generate electricity based on varying factors like sunlight, wind speed, and tides. This inherent variability leads to intermittent power generation, making it difficult to match supply with demand consistently. The intermittent of renewable energy creates imbalances in the grid, which can result in energy waste, grid instability, and reliance on backup power sources. To overcome these challenges, effective energy storage systems play a pivotal role. Renewable energy storage, grid stability and reliability. Energy storage systems provide stability to the grid by smoothing out the variability of renewable energy generation. They store excess energy during periods of high production and release it during periods of low or no generation, ensuring a consistent power supply and reducing grid stress. Possible integration of renewable energy sources in various desalination technologies. Renewable energy harnessing could use geothermal, ocean thermal, solar thermal, or industrial waste heat into thermal energy. This is used in the desalination process in phase change processes. Variable renewable sources and integration. Renewable energy storage enables the integration of variable energy sources like solar and wind into the grid. Excess energy generated during peak production periods can be stored and utilized during periods of low or no generation, ensuring a steady supply of electricity. Energy management and flexibility. Energy storage solutions offer enhanced energy management capabilities, allowing for optimized utilization of renewable resources. They enable power providers to balance supply and demand, store energy during off-peak times for use during peak demand, and support the grid during sudden changes in generation or consumption. Resilience and emergency preparedness. Energy storage enhances grid resilience by providing backup power during blackouts or disruptions. It offers reliable and immediate power supply, reducing dependence on traditional backup systems and fossil fuel-based generators. There are several ways to increase grid flexibility and improve the integration of renewable resources. Energy storage can be paired with variable renewables to accommodate fluctuations in renewable generation over the course of the day or several days. Electricity can be stored during times of high generation, for solar, during sunny days, for wind, during times of high wind speeds, for later use during periods of high demand. Building more transmission lines to connect areas endowed with plentiful renewable resources, e.g., very sunny or windy areas with areas of high electricity demand, can increase the value of renewable resources and reduce uncertainties of their electricity generation. For example, building solar plants in deserts that get sunshine most of the year can reduce weather-dependent uncertainty associated with the system's production. Combining different renewable sources can balance out variability of production of one resource type. For example, a grid that relies on many types of renewables such as solar, wind, hydro, and geothermal altogether will likely face less volatility in production than one that relies exclusively on wind energy alone. Demand-side management can be used strategically to optimize the times when electricity is used to reflect the availability of generation. Demand-side management can include shifting flexible demand to times of high renewables production, such as preheating electric hot water heaters or charging electric cars during times of high solar energy production, and reducing demand during peak hours, thereby lessening the slope of the ramp. Placing value on generator flexibility in the wholesale power markets can encourage grid flexibility. California, for example, has attempted to manage its duck curve through the development of a flexible ramping product that compensates generators for their ability to ramp quickly. Options like this allow the market to decide how to best enable flexibility, rather than prescribing a set solution. Innovative renewable energy storage solutions. Battery energy storage systems. Best lithium-ion batteries, such as those used in electric vehicles, have become increasingly popular for energy storage applications. These batteries are scalable, modular, and capable of quick response times, making them suitable for both residential and grid-scale storage. Additionally, advancements in battery technology are driving down costs and improving performance. Pumped hydro storage. Pumped hydro storage is one of the oldest and most mature energy storage technologies. It involves pumping water to an elevated reservoir during periods of excess electricity and releasing it through turbines to generate electricity when demand is high. While geographically dependent, pumped hydro storage offers large-scale storage capacity and long-duration capabilities. Thermal energy storage. Thermal energy storage systems store heat or cold generated from renewable sources for later use. This technology is particularly useful for applications such as district heating, industrial processes, and HVAC systems. By storing thermal energy, renewable generation can be decoupled from immediate consumption, improving efficiency and reducing energy waste. Power-to-X technologies convert surplus renewable electricity into other forms of energy or products. For example, power-to-hydrogen produces hydrogen through electrolysis, which can be used for transportation or industrial purposes. Power-to-X solutions enable the conversion of excess renewable energy into storable fuels or feedstocks, offering additional flexibility and value. Advanced grid management systems. Intelligent grid management systems leverage digital technologies, artificial intelligence, and machine learning algorithms to optimize the integration of renewable energy and storage. These systems forecast renewable energy generation, manage grid imbalances, and dynamically adjust energy flows, maximizing the utilization of renewable resources and storage capacity. Renewable energy storage solutions are instrumental in overcoming the intermittency challenges associated with renewable energy sources. By enabling grid stability, optimizing energy management, and supporting emergency preparedness, these solutions pave the way for a sustainable and reliable energy future. Continued advancements in storage technologies, coupled with supportive policies and investments, will further accelerate the integration of renewable energy and storage, driving us closer to a cleaner, more resilient, and sustainable energy system.